Hello, everybody. I'm happy to share our research entitled The Framework for Optimizing Negative Emission Technology or NETS Portfolios. My co-authors are Professor Raymond Tan and Professor Kathleen Aviso. My name is Maya Victoria Sumagang, and I'm a faculty of UPLB and a PhD candidate at De La Salle University. Let's begin with the introduction. There is undeniable scientific evidence that human-made emissions are causing global warming. And the modeled pathways that limit global warming to 1.5 degrees requires the emissions to peak by the year 2025, which is less than 2 to 3 years from now, and to reach net zero by the mid-century. And this is from the IPCC report. Without our mitigation efforts, the global warming will cause severe climate impacts that will cause billions of dollars in economic loss and will make it difficult for humans to thrive. The same IPCC report also listed strategies to counter climate change, and this includes renewable energy, carbon capture and storage, demand side measures, improving efficiency, and now we have negative emission technologies. And nets remove carbon dioxide from the atmosphere for storage in a different environmental compartment, like underground or in biomass. Before, nets were still optional, but because of the delay in climate action, that time has passed. Nets are now needed to counterbalance the residual emissions to reach net zero, especially because we have difficult to decarbonize industries like aviation, heavy transport, etc. One of the challenges in the large-scale implementation of any decarbonization portfolio, like NETs, is that they have environmental footprints, meaning they will consume resources such as land, water, energy, nutrients, and even cost. And to be able to deliver the required negative emissions. The IPCC report recognizes the possible negative impacts of the wide-scale implementation of these technologies on biodiversity, water and food security, and livelihoods. Hence, the systematic planning of these technologies is critical for their successful implementation. Particularly, portfolio solutions are better because of their lower risk and lower environmental impact, but there is currently a gap in the computational decision support for the strategic deployment of nets. And studies have suggested using the planetary boundaries and the United Nations Sustainable Development Goals as frameworks in planning and assessing nets. But very limited studies have been found investigating net portfolios under these frameworks. And also, nets have also other aspects such as time limitations and synergistic interactions that are not included in this framework that are very important to be considered in the framework for their planning. Few studies have been published on net portfolio optimization under resource constraints, and these studies do not consider all the aspects that I've mentioned earlier. So to address all of these research gaps, this study aims to develop a modeling framework for the large-scale implementation of nets. And finally, to demonstrate this framework in a case study which showcases all the aspects mentioned. Moving on to the methodology, this is the proposed modeling framework developed in this study, which is actually part of the results of this study. So the first box identifies the challenges encountered in net portfolio modeling. And these are the existence of multi-footprint constraints, time or temporal constraints, and because some nets are not technologically ready yet for large-scale implementation, so they have different time constraints. They also have synergistic resource interactions. Some nets consume fewer resources when implemented together. And finally, they also have epistemic uncertainties. The second box identifies the modeling approaches that can handle these challenges. So incorporating these challenges in the model using optimization techniques give rise to the recommended net portfolios. So for this study, mathematical programming was chosen as the technique in optimizing the net portfolio since it can handle large and complex optimization problems. A mathematical program consists of an objective function, equality and inequality constraints, and also it can have continuous and integer variables. The mathematical formulation based on the framework shown earlier is shown. So first, the base model addresses the multi-footprint aspect of the nets. Then model developments are built on top of the base model, increasing the complexity. For this study, we are now at the final stages of the work, wherein this is the most complex model yet, considering all the aspects mentioned. On the left side is a snippet of the mathematical program developed for this case study. But for the sake of time, I will not go to the details of the program. For the illustrative case study demonstrating the framework, 6 terrestrial nets were considered, namely bioenergy with carbon capture and storage, afforestation, reforestation, soil carbon sequestration, biochar, direct air carbon capture and storage, and enhanced weathering. The footprints were obtained from recently published literature, and the resource limits were based on the ASEAN region resource limits, and also the prices of each net were also based from recently published literature. Anyway, I have put the references in case you're curious to find out about the data sources. So this is just a glimpse of the data used for this case study. Moving on to the results and discussion. So the mathematical programming gave rise to a mixed integer nonlinear programming model, which is, we also call it MINLP. And it considers all the aspects mentioned, the multi-footprints, temporal constraints, synergistic interactions, and uncertainties. The results of the model is shown. So the ASEAN region can deliver a cumulative negative emissions of 36.48 gigatons of carbon dioxide from the year 2030 to 2100. And afforestation and biochar are consistently in the portfolio. So, and they have corresponding capacities of 9.08 and 6.88 gigatons carbon dioxide respectively. Direct air capture begins at the year 2040 and will ramp up as a major negative emission source by the year 2050. And then the peak negative emission potential occurs between the years 2050 and 2060. So the results are consistent with the integrated assessment models that show peak GHG reduction by the mid-century, but they differ with previous studies because this portfolio prioritizes direct air capture over enhanced weathering. So the results simply The results imply that in a resource and time constrained simulation that considers uncertainties, direct air capture plays a major role in negative emissions starting in the mid-century. And the total net present value of the portfolio is 992 billion US dollars. Moving on to the conclusion. So this study developed a framework for NET's portfolio optimization, and it has four critical aspects: the footprint, temporal constraints, synergistic interactions, and uncertainties. It was demonstrated in an illustrative case study using mathematical programming. This work supports the analysis of decarbonization portfolios. Future work may include adding new features in the framework, such as antagonistic resource interactions between nets. Thank you very much. We have now reached the end of the presentation. Comments and questions are welcome, or you may also email me at this email address.